Lesson 6.2, Dot product of vectors. Now, this section has to do with another vector operation. We talked about some vector operations in section 1. Specifically, we talked about vector addition and scalar multiplication. Vector addition, again, was just when we add two vectors together. And of course, add or subtract, because subtraction is just addition of negative numbers. And if we add or subtract two vectors, the answer is still going to be a vector. Likewise with scalar multiplication, that's when we multiplied a scalar times a vector. Remember that a scalar is just a magnitude, whereas a vector is a magnitude and direction. So if I take a magnitude and multiply it times a magnitude with direction, I get another magnitude with direction, but the new vector is either going to be longer or shorter than the original vector by a factor of whatever that scalar was. Now, scalar multiplication is not the only type of multiplication when it comes to vectors. Now, as far as scalars go, regular old numbers, when I say multiply, there's only one way that you can multiply. There's 7 times 4 is 28. There's no other way to do it. Of course, I could do 4 times 7, but that's not a different way. That's the same way, just reversing the order. We also have two more types of multiplication when it comes to vectors, a dot product and a cross product. Now, a dot product focuses more on the magnitude of the vectors, whereas a cross product puts everything together. With a dot product, we take a vector times another vector, and we get a scalar as an answer. If we, anytime we're trying to multiply two vectors, but we want to focus more on their magnitudes, then we would do a dot product because we would get a scalar or just a magnitude as our answer. As opposed to a cross product is when we multiply vectors and get a vector as the answer. Now notice the notation. Dot product uses a dot, cross product uses a cross. In elementary school, you may have been told that these two symbols meant the same thing, and it's just personal preference as to whether you use a dot or a cross to imply multiplication. That is not true. Much like most of the things your elementary school math teachers would tell you, most of what they say was simply just so that you wouldn't question it and we could just move along because it wasn't important at the time. Well, now that we are in upper level mathematics, it actually does become important. There is a difference between a dot and a cross. A dot product produces a scalar answer, a cross product produces a vector answer. Now, of course, it also entails completely different techniques of multiplication. Just like with scalar multiplication is one type of multiplication. Well, dot and cross product are two other types of multiplication, that all three of which require completely different techniques. Based on the notation that you presented, you know which technique to follow. Now, we are going to be focusing on dot products today. If we have time, we may talk about cross products, but cross products really don't become important until you get into three-dimensional geometries. Because a cross product, the answer is going to be perpendicular to the original vectors. And the only way you can kind of have a vector that's perpendicular to the original two vectors is that it be in the third dimension. In other words, if I draw two vectors on the screen, the cross product vector would be another vector coming out of the screen, perpendicular to the screen itself. So let's start with a dot product. So let's consider two vectors, AB and CD. All right. If I want to get a dot product of vector u and vector v, it has to do with pulling out their magnitudes. Now, it technically doesn't matter which way I do this, whether I take the magnitude off of u or take the magnitude off of v first. But really, what we do is we start with leaving one of the vectors completely alone. In this case, I'm going to leave v completely alone, and I'm going to manipulate u. Now, I want to take the magnitude off of u. Now, what I'm not saying is I want the magnitude of u. I want to take the portion of the magnitude that's going in the same direction as v. In other words, it's just like breaking a vector into its component form. It has an a component, it has a b component, it has an x direction, it has a y direction. But I'm not breaking it into the x direction, y direction in terms of the axes. I want to break it into the v direction. And I can do it the same way I normally do. Consider the angle between the two vectors, and consider a right triangle dropped from vector u perpendicular to vector v. So remember, x-axes and y-axes are completely irrelevant. They're arbitrary and simply give us a frame of reference. I can drop a perpendicular in any direction I want to as long as it's perpendicular to something. This is also called a projection. Now imagine I have like a lamp sitting above the screen shining some light in this direction. The vector u would cast a shadow on vector v right here, right along the base of the right triangle. That red line right there is referred to as the projection of u onto v. There's a fancy little notation for that. That would be the u sub proj for projection. So that red line would represent the projection of u onto v. And the measure, the length of that u projection onto v, is simply using right triangle trigonometry. Here's my angle. The projection is the adjacent side. The magnitude of u would be the hypotenuse. So just like we do with component form, I can just take the magnitude times the cosine of the angle, and that would represent that length of that projection. And for a dot product, I'm going to take that quantity and multiply it times the magnitude of vector v, because both of these quantities are going in the same direction, so I can multiply them. The projection of u and the actual vector v, same direction, so I multiply them, so there's my dot product, and I would just clean it up and write it like this. So dot product of u and v is really the magnitude of u times the magnitude of v times the cosine of the angle between those two vectors. Not the angle with respect to the x-axis, but the angle between those two vectors. Now this formula is all well and good, but it's actually not the formula we typically use. Let's go ahead and clean this formula up. So I'm going to take that formula and I'm actually going to write it in a much simpler way, but it's going to take a little bit of work to get it to that much simpler way. So first thing I'm going to do is I'm consider that angle between the vectors. I'm going to realize what that angle really was. Well, that angle theta really could be found by taking the real angle for u, not the angle between theta, but the angle with respect to u, and the angle for v. If I take the angle for u and subtract the angle for v, then that would give me the angle between. Alright, if I just take the angle that standard position angle for u and the standard position angle for v, subtract, I get the angle between those two vectors. So really I could take that theta and break it up into theta u minus theta v. Well, if we remember back to chapter 5, this right here is now a cosine difference of angles. I can use my cosine difference formula to expand that. So if you can't remember what that was, you can look back in your notes or look back in a book. I'll give you a second to see if you can remember what it is. Press pause if you need to. Alright, if you haven't been able to remember what it is, hopefully it'll jog your memory when I do it. Cosine of a difference angle, so remember with the cosine formula, it was cosine, cosine, sine, sine. So I'll do cosine of theta with respect to u times the cosine of theta sub v. Now remember, with cosine, if it's subtraction over here, then it's going to be addition over here. And then it's going to be sine, sine with the two different angles. So there's my cosine expanded. Now I realize that that magnitude of u and magnitude of v can be distributed across this summation. So I give it to both the cosine group and the sine group. And then what I'm going to do is I'm just going to creatively reorganize things. This is the step that separates the mathematicians from the non-mathematicians. If you wouldn't think to do this, that's fine. This is one of those things that takes a little bit of creativity, and creativity comes with lots and lots of practice. I'm simply going to rewrite the order of these terms. I'm going to take this magnitude of v and move it to the middle, because what I've really done here is created something. The magnitude of u times the cosine of theta sub u, that right there, if we remember correctly, magnitude times cosine of the angle, if we go all the way back to our u vector, that's the formula that we use to get the component form of a vector. Magnitude times the cosine of the angle, magnitude times the sine of the angle. So that right there represents the a portion of our u vector. Just like over here, u sine of theta sub u, that's the b portion of our component vector. And we can do the same thing with the v vector. Magnitude of v cosine of theta sub v, magnitude of v sine of theta sub v, and that one represented c and d. Remember, we're using vector u, which was ab, vector v, which was cd. So by manipulating this in this way, really I've got a much simpler way to get my dot product. It's just AC plus BD. Whatever the components are for U and V, AB being the component form of U, CD being the component form of V, I just have to multiply the X components, multiply the Y components, and add them together. Just to recap, multiply the X components, multiply the Y components, add them together. A much simpler way to evaluate a dot product. Now, of course, I could still use that other formula, magnitude of U, magnitude of V, cosine of the angle between, but then I would have to go through the process of figuring out what's the magnitude of U, what's the magnitude of V, what's the angle between, and then multiply all that together. Meanwhile, I would have been done with this long before. Alright, let's practice. So we have vector R is at 2, -5, vector S is at 1, 4. We'll start with the dot product of R and S, then 2 times R dot product with S, and then the vector S times the dot product of S and S. Go ahead and give these a try on your own first. Alright, so R dot S, I'm going to take vector R, which is 2, -5, vector S, which is 1, 4, and we'll do our dot product. Remember, to do the dot products, it's just going to be the X components, 2 and 1, multiplied together, and then the Y components, -5 and 4, multiplied together. So 2 times 1 is 2, -5 times 4 is 20, or -20. And then the part that most of us forget when we're just starting to learn this, we have to add them together before we're done. -18 is my final answer. Don't leave it as a vector to -20. That's not what we're doing. We're not just multiplying like we did with vector addition and leaving it as a vector. We have to add those numbers together when we're done to get our final scalar answer. Alright, now for part B, all we have here is the same thing we had in A, but with a 2 up front, a scalar multiple of 2. So easiest way to do this problem was simply to take my answer in A and double it. -36 should be my final answer. Or if you want to, you can do it the long way, or if this was the only question you had, you can do it this way. Now that 2 can apply to either the R or the S. It really doesn't matter. Remember, when we're multiplying A times B times C, you can either multiply A and B or A and C, just don't multiply it to both. So I'm going to go ahead and apply that 2 to the R to make it 4, -10, dot 1, 4. 4 times 1 is 4, -10 times 4 is -40. Put it together, -36, just like we expected. Now the last one, remember, just follow the order of operations. We'll be fine. Do the parentheses, what's inside the parentheses first before you deal with the S on the outside. We'll do S dot S, which just means take 1, 4 and multiply it by itself. 1, 4 dot 1, 4. So 1 times 1 is 1, 4 times 4 is 16. Put it together, we get 17. Not my final answer because I still have to take that 17 and multiply it times the vector S. So when I do that, it's now really a scalar multiplication, so I'm going to get 17 times vector 1, 4, which is 1768. On this one, I had 3 vectors being multiplied, so it makes sense that I would have a vector as my answer. It's just like if I have 2 negatives, I get a positive, but if I have 3 negatives, I have a negative. 2 vectors, I get a scalar. 3 vectors, I would be back to a vector. Angle between 2 vectors. So we addressed that angle between the 2 vectors before when we were defining the dot product, but it actually allows us to establish an alternative way to finding that angle between 2 vectors using the dot product. So instead of using the angle to figure out what the dot product is, we can use the dot product to figure out what the angle is. Now, there are really 2 options to do this. Obviously, the first way I addressed earlier was just to subtract the 2 angles, the angle for U and the angle for V, and I would get the angle between. But I personally don't like that method because A, I have to do 2 separate problems. B, I have to be very careful which quadrant those vectors are in, because if they're both quadrant 1, great, that's fine, super easy. But if say one's in quadrant 1 and the other one's in quadrant 2, 3, or 4, or maybe both of them are in quadrant 2, 3, or 4, then I have to worry about not only my inverse tangent rule, but also my adjustment. I better make sure I make the correct adjustment, and it just gives me too many variables that I could screw up. By using the dot product formula, the original dot product formula, it gives me one nice simple formula that I can just plug straight into the calculator and get the angle between 2 vectors. Now remember that original dot product form was magnitude of u times the magnitude of v times the cosine of the angle between. So if I'm looking for the cosine, or looking for the angle between, let's just solve for the cosine. Now, of course, I could go one step further and solve for the theta, but it's, for some reason, it's just more common to write it like this. If I'm trying to solve for theta, I'm just going to take the inverse cosine of both sides. But notice it's cosine of theta, dot product on top, product of their magnitudes on the bottom. Alright, let's practice that. Find the angle between vector x, which is at 2, 7, and vector y, which is negative 1, 5. So remember, I'm going to start with my formula, and I just got to plug things in. I'll start by doing the dot product using the quick little arithmetic. I could even do that in my head if I wanted to. And on the bottom, I'm going to do the magnitude for u and the magnitude for v. In this case, u and v represent x and y. Alright, so let's start with the top, the dot product. So cosine of theta equals, on the top it's going to be 2 times negative 1, which is negative 2, 7 times 5, which is 35, and I'm going to have to add those together. I'll clean that up in just a second. Let's go ahead and do the bottom as well. I need the magnitude of u, or the magnitude of x, which is just going to be the square root of 2 squared plus 7 squared. And of course the magnitude for y is going to be the square root of 1 plus 25. Now before we do anything with the calculator, let's go ahead and clean this up as much as we can. On the top I'll get 33. And on the bottom I'll have the square root of 53 and the square root of 26. But the way I'm actually going to write it, I'm not going to write those roots separately. I'm going to realize that if I'm multiplying two roots, that's the same thing as just multiplying what's inside the roots. The square root of a times the square root of b is really the square root of ab. So I'm going to go ahead and rewrite it as 53 times 26. Now I want to point out, at this point, everything I've done has been in my head. I have not grabbed a calculator, and hopefully you didn't need a calculator for any of this either. If I wanted to do 53 times 26, I would need a calculator. So because I would need a calculator for it, I'm not going to waste time calculating it, because I know I definitely need to get a calculator to figure out theta. So instead of grabbing the calculator twice, I'm just going to grab the calculator once. I'm going to leave it as 53 times 26 until I'm ready for the calculator, which happens to be right now. So let's go ahead and solve for theta. And I'm going to solve for theta by simply moving the cosine to the other side as an inverse cosine. And this is what I'm going to type into my calculator. I'm going to type the inverse cosine of 33 divided by the square root of 53 times 26. Now again, you could do 53 times 26 as a separate problem so that you can figure out what that is. I personally think that's a waste of time. I'm just going to type this in my calculator exactly as is and let the calculator do all the work all at once for me. Now, be careful with the parentheses. That root is going to have parentheses around it, just like you're going to need parentheses around the entire fraction. So when you type it into your calculator, it should look something like this. I've got that initial parenthesis for the inverse cosine. I've got the 33. The top of the fraction doesn't need its own set of parentheses because there's only one number there. The bottom of the fraction has multiple numbers, so technically I need a set of parentheses for it, but the root acts as its own set of parentheses. So that'll be the parenthesis that comes automatically with the root. 53 times 26, close the root, close the cosine, 27.255 degrees for the angle between those two vectors. Now, feel free, if you want to double check this using the inverse tangent method. 2, 7 is in the first quadrant, negative 1, 5 is in the second quadrant. I would make a 180 degree adjustment on the y vector, and then I would just subtract the angle for y from, or minus the angle for x, because the angle for y is definitely going to be larger than the angle for x. You should get the same answer. If you like that method, you can use it. This is the one I like because it's just one formula, one process, all packaged together. Alright, here's another one for you to try. Try it on your own and then see how I did it. Alright, so find the angle between 5, 8 and negative 4, 2. We'll start with the formula. We'll figure out the dot product first. 5 times negative 4, which is negative 20. 8 times 2, which is 16. On the bottom are magnitudes, square roots of 5 squared and 8 squared would be 25 and 64. 16 and 4 for the other one. Add it together. Negative 20 plus 16 would be negative 4. On the bottom we have 20 and 60 is 80 plus 9, so 89 and 20. Inverse cosine, type it in the calculator just like the previous one. and we should end up with 95.440 degrees. Now, this topic leads us directly into our next topic, which is something concerning the word orthogonal. Orthogonal, one of those fancy math words that makes you sound smart, but really is not that complex. Orthogonal just means perpendicular. It's just a word that specifically has to do with vectors. We wouldn't say that two lines are orthogonal. We would simply say two lines are perpendicular. But if it's vectors that are perpendicular, we prefer to use the word orthogonal to be more specific. Now, orthogonal, again, means perpendicular, so it means the angle between the two vectors is 90 degrees. So what that means is, if I were to use that angle between two vectors formula, plug in 90 degrees for cosine, well, cosine of 90 is 0. The only way a fraction is ever going to equal 0 is if the top equals 0. So that really means that the dot product is 0. So what we now have is a connection between being orthogonal and the value of the dot product. If it's orthogonal, the dot product is 0. If the dot product is 0, then it's orthogonal. We have a theorem. If u dot v equals 0, then the vectors are orthogonal. So in other words, if I ask you, are these two vectors orthogonal, the way we answer that question is we do the dot product. It's very quickly, we can very quickly do it in our head. 5 times negative 6 is negative 30. 2 times 15 is positive 30. Add it together, we get 0. Therefore, those two vectors are orthogonal. Now, we're talking about perpendicular, might as well go ahead and talk about parallel as well. Now, we could technically use the same technique to figure out parallel. Instead of it being a 90-degree angle between, it would be either 0 or a 180-degree angle between the vectors. That would mean that they are parallel. Now, it's important to establish, again, obviously if there's a 0-degree angle between or 180 degrees, you would think to say, well, shouldn't those vectors be right on top of each other and thus are not parallel? Well, that's only if you're considering the ones that are in standard position. Remember, I can move those vectors anywhere on the screen and they still be the same equivalent vector. So the concept of parallel has to be a little different here, where it's not so much that they don't touch, it's simply that they're going in the same direction. And the way, but a simpler way that we can know that instead of having to worry about the angle is that if one vector is a scalar multiple of the other, in other words, u is equal to k times v. In other words, if I just take one vector and make it bigger or smaller, or longer or shorter, then that vector is parallel to the original vector. So 2, 3, and 6, 9, I want to know, is one of these just a multiple of the other? Now, sometimes you can just eyeball something like this, but if they're ugly decimals, I wouldn't recommend it. If I want to know if one is a scalar multiple of the other, let's just go ahead and double check term by term. I can take 6 and divide it by 2. I can take 9 and divide it by 3. If I get the same answer on both, then I know that there was a value for k that I actually distributed across when I was multiplying it. Therefore, since these both have the same fraction, then yes, they are parallel because, of course, 6, 9 is just the scalar multiple of 3 times the vector 2, 3. Alright, here are a couple of vectors. Instead of me giving you in component form, I went ahead and switched to the linear combination of standard unit vectors. Are the given vectors parallel, orthogonal, or neither? One of those classic geometry questions that we haven't asked in a while. Here it is, parallel, orthogonal, or neither. Give it a try. Alright, so on the first one, if I want to know if it's parallel, orthogonal, or neither, it's basically just like you did in algebra and geometry. We can go test by test to see which one works. I always like to start with the dot product to check to see if it's orthogonal. So I'll do my dot product on R and S. Remember, multiply the A components, multiply the B components, and add it together. So 2.3 times 10.2, 3.4 times negative 6.9. I'm going to get 23.46 for the first pair, negative 23.46 for the second pair, which tells me that these are orthogonal. No need to check anything else because I've got my answer. Alright, let's try this one. Same deal. I'll start with the dot product. 5.1 times negative 2.5 is going to be negative 12 3/4. Negative 6.2 times 3.1 is going to be negative 19.22. And don't waste time trying to figure out what the answer to this question is. Don't waste time pulling out the calculator to do the subtraction. The goal is it parallel, orthogonal, or neither? My current test is checking for orthogonality. The answer is definitely not 0, so it's not orthogonal, and I'll move on. Next thing I'll do is I'll check to see if it's parallel. The way I check to see if it's parallel is I just divide. Divide the A components, divide the B components. Well, on the A side I get 2.04, or negative 2.04. On the B side I get negative 2. Close enough, you might think, but not quite. There is no such thing as close enough. It either is or it isn't. This one isn't, therefore neither would be my answer. Alright, here's a fun one where it seems like what we just did may not be related, but in fact it is directly related. I want to find the interior angles of the triangle with vertices -4, 1, 1, -6, and 5, -1. So I'll start by drawing this triangle by plotting those vertices and connecting the dots. So there's -4, 1 in the top left, I've got 1, -6 on the bottom, and 5, -1 on the right. So there's my triangle, and I want to go angle by angle, and I'm going to figure out their measures by realizing that these sides to the triangle could actually be represented with vectors. For example, these two sides would be these two vectors. So if I'm going from 1, -6 to 5, -1, think of 1, -6 as my initial position, 5, -1 as my terminal position. So if I wanted to get the component form for that vector, it's just final, or head minus tail. 5 minus 1 would be 4, -1 minus -6 would be 5. So that's the vector 4, 5. And then for the other vector, I can use these two coordinates where -4, 1 would be the head, 1, -6 would be the tail, -4 minus 1 is -5, 1 minus -6 would be 7. So here are my two vectors, and the question is to find the interior angle, so I can use the angle between two vectors formula to find this angle right here. So we'll start with -20 plus 35 on the top, 25 and 49, 16 and 25 for the magnitudes of each of those vectors. Clean it up, type it in, 74.197 degrees. So there's my angle right here. Why don't you take the next angle? We're going to do this angle right here. Give it a try, see what you can do. Alright, so for this one, I'll go ahead and start with the bottom vector. Terminal final position will be 1, -6. Initial was 5, -1. So final minus initial, 1 minus 5 is -4. -6 minus -1 would be -5. And then on this one, -4, 1 minus 5, -1. So that would end up being -9, 2. And we'll find the angle between those two vectors. Dot product is 36 minus 10, 81 plus 4 on one side, 16 and 25 on the other side. Clean it up, type it in, I get 63 and change. So this angle was 74, this angle was 63. Now of course we could do the whole vector process again for the third angle, or we can realize it's a triangle, subtract from 180. So that our final answer was 41.933.